we want to perform a short wavelength and long wavelength time series observation. Now, in a nominal case, we would love high signal to noise for our short wavelength data, which would typically mean more spectra and longer readouts. But we also want to avoid saturation for the long wavelength data, which probably means we want shorter readouts or less short wavelength spectra. The issue is if we make our readout too short, then we're recording a much larger amount of data, and we need to avoid large data excesses. And this is actually quite a considerable issue compared to some of the nominal sort of readouts you might be familiar with. And we're able to really exceed the data excess in durations less than a typical transit duration. So here's an example of this here, where you kind of have an example of the data volume you're getting versus your scheduling and how much your nominal data allocation is. Really, you can't be pushing into these warning zones. Sometimes this yellow warning is okay, which is around sort of 5 gigabytes per hour excess. But if you're bumping into the sort of 15 gigabytes per hour, then you're really going to struggle to schedule your observations. And to some degree, they might just be unschedulable. And like I said earlier, for rapid readout, so this is the fastest readout NIRCam has with 2 groups, you can quickly exceed this lower yellow threshold in just 1 to 1.5 hours. So really, definitely not long enough for a typical transit observation. And we need some kind of alternative. So here at ST, there have been new readout patterns designed to specifically avoid these data excesses. And the way they do that is they progressively add more and more skipped frames to your readouts so that you're getting a longer ramp based on what kind of length of ramp you want, but you're skipping more of the frames. So less frames are being explicitly recorded to the detector, but you're still getting the sort of same length of ramp. And people who are familiar with the longer readout patterns like medium, shallow, and deep will be quite familiar, I think, with these skipped frames. So as an example of that, I can show a ramp for the DHS3 readout pattern. So these are the kind of patterns we've added, DHSN. And 3 here is the number of frames that are being read out. And the number of skipped frames is always 1 less than that number. So here for DHS3, we go up our ramp, we've performed our reset, we take a read, we then skip 2 reads. So the ramp's still counting, the detector is still building up counts, but we're just not recording it to disk. We perform another read and we repeat up our ramp until we've reached the number of groups we wanted to use for this readout pattern. So you can see we've managed to cut off a significant portion of our data volume just by not recording these reads, but we're still sort of getting a similar ramp in terms of the signal on the actual detector. So just coming back here for a second, I want to emphasize these readout patterns are available prior to scheduling of cycle 4, but they are not currently in the APT. So if you prep your observations, or the ETC, I should say, if you prep your observations, you're not going to have a direct toggle to sort of switch this on and off. But we will show you some slides later on where you can kind of approximate these readouts using the rapid readout mode. So just to touch on saturation a little bit, now we still want to balance this data excess and our reads against our long wavelength. Now, this chart here is quite big. I'll break it down for you. It's the exposure pattern we're using, the number of groups in that exposure pattern that we're applying to our integrations, and then the data excess rate we get in gigabytes per hour for the different subarrays. So in this case, we have sub 40S2. This is if you're extracting 2 spectra, 4 spectra, or the 2 8 spectra options. And then on the right, we have the same representation essentially, but instead of excess rate in gigabytes per hours, we have the hours to exceed that lower threshold of 5 gigabytes. And you can see here, for the rapid readout, our excess in just 1 hour is 6 gigabytes. We're already over the lower threshold, and you can see that here, 0.8 hours. So really not sufficient to perform the kind of observation we would typically want to apply. But as we move to longer readouts, and particularly these new DHS-N readout patterns, those data excess rates kind of get suppressed, and we can eventually reach a point where the data excess rate is negative, and we can perform essentially an infinitely long exposure. The only caveat being is as you move down on this chart, you make your ramps longer. And by making the short wavelength ramp longer, you have to make the long wavelength ramp longer. So you have a higher chance of long wavelength saturation.